Hello, my geeslings. It's Mother Goose Robinson. This is episode 30 of Robinson's podcast, and it is my second episode with David Albert. He's a philosopher of physics at Columbia University in New York, and one of, if not the world's leading philosopher of physics. And not only is he so bright and knowledgeable on all of these issues, but he's also just such a great teacher. And you really get this from listening to the conversation, or in my case, from talking with him. So in this conversation, we talk about ancient physics and how it is related to contemporary physics. Then we go through this sort of continuum that he draws between theoretical physics, foundations of physics, philosophy of physics, and metaphysics, and how they're all related. Then, for most of the conversation, we talk about time and scientific anti-realism and his course that he's teaching at Columbia this semester called, well, I'm not sure if it's Time's Arrow or the Arrow of Time, but it's about the directionality of time and how we seem to perceive it as moving in a certain direction. And at the end of the conversation, we talk a bit about metaethics. He identifies as an expressivist, and we talk about how that relates to the naturalistic project. Anyway, I hope you enjoy this episode. I got so much out of the conversation, and I got even more out of listening to it a second time. And I'm already really excited to have David back again in the near future. Yesterday, I spoke with a Stanford professor, Christopher Babanich, who does ancient value theory. And it occurred to me that even though I'm also taking a course on ancient physics with Alan Code, contemporary physicists, to my knowledge, aren't referencing Aristotle, or contemporary physicists aren't either, contemporary biologists, psychologists, and yet physics is an ancient discipline. It's extended from antiquity to the present, but ancient ethics is still relevant today because we're still going through the same sort of problems we were going through back then, just dealing with people in interpersonal commerce. And I was wondering if philosophy of physics is different. Are you still referencing Aristotle or Zeno or other ancient physicists in your work? Do they still play much of a role in your thinking about time or space or anything else?
Hmm. I mean, it doesn't, I'm not sure what to say. Yeah, I don't think, um, I don't think ancient stuff is nearly as absent from, um, uh, there's this sort of continuum from theoretical physics to what people call foundations of physics to what you might more properly, or in an old-fashioned sense, call philosophy of physics, to metaphysics proper. And on the sort of philosophy of physics, metaphysics, and um, uh, classical figures, ancient figures, enter much more into the discussion than they do on the sort of foundations of physics, theoretical physics end. Certainly, people are interested in the kinds of questions raised by Zeno. Certainly, people are interested in how they should think about infinities and Aristotelian positions or Aristotelian sorts of questions about whether infinities are to be thought of as actual or literal or existent or merely potential or something like that are there in the background of considerations about sort of what the concept of a limit is about in calculus and so on. So and and there are people around with more Aristotelian notions of causation. There are people around with more Aristotelian notions of the difference between the past and the future. So yes, that stuff I wouldn't say that stuff is altogether absent from modern speculation in philosophy of physics, in foundations of physics, and certainly in the areas of more straightforward metaphysicsy stuff that's in dialogue with philosophy of physics and foundations of physics.
Okay, well, as I mentioned to you before, time is largely what I wanted to talk about today. Mm-hmm. And I had never heard of this spectrum or this continuum you mentioned, going from theoretical physics to foundations of physics to philosophy of physics to metaphysics. And I'm a bit curious, or I'm very curious about if you could tell me a bit more about this spectrum and where, I mean, if it's a continuum, there might not be dividing lines.
Yeah, I don't no, there certainly aren't dividing lines. I mean, I think that it's precisely what's been interesting and fruitful and exciting in foundations of physics over the past 50 years or so.
Well, I don't know what foundations of physics necessarily means.
Good. There are all sorts of questions at the conceptual foundations of physics, where foundations there just means exactly what you think it means. It's not as if, so let me put it this way. There are all sorts of questions at the conceptual foundations of physics, particularly so in connection with quantum mechanics and with the measurement problem in quantum mechanics, where the distinction between doing a more scientific kind of work and a more philosophical kind of work began to dissolve in all sorts of ways that I thought of as interesting and fruitful. That is, once upon a time, what people used to do in what was called philosophy of physics was take some finished physical theory, like, for example, the general theory of relativity, or like Newtonian mechanics, or something like that, and try to analyze its logical structure, try to analyze its conceptual foundations, try to draw metaphysical consequences from it, to use it to support or to critique various kinds of metaphysical theories about what there is in the world, so on and so forth. The disciplines of doing the theoretical physics and doing the philosophy of physics were fairly well demarcated from one another. With discussions of the foundations of quantum mechanics over the past 50 years or so, especially around the measurement problem, I would say one of the important achievements of the past 50 years of thinking about the measurement problem has been the capacity, has been the understanding that this is in fact a scientific problem, which is going to require some modification of our fundamental scientific theory in order to solve. And but the question of exactly what sorts of modifications would count as solutions, what you wanted of a solution to this problem, were questions that required a considerable amount of philosophical sophistication to make clear. Okay. So you have, something funny that happened around the measurement problem is that it was widely regarded by physicists as not a scientific problem, as some kind of a verbal problem at worst, or at best a purely philosophical problem, whatever that means. And a lot of what philosophers contributed to this discussion over the past 50 years was to argue that it was not a philosophical problem, that it was a scientific problem, and that an adequate solution to this problem was going to require a modification of the fundamental equations of motion of the world, okay, or something like that. It was going to require a modification in our basic scientific theory, a modification which would probably carry with it new empirical predictions, and so on and so forth. And it was in the funny way that the dialectic went throughout the course of especially the second half of the 20th century, what was going on is that it was philosophers who were in the main trying to press the point that this was not a philosophical problem, that this was a scientific problem. But the business of recognizing that was something that it turned out philosophers were in a better position to see than physicists were in a position to see. So you encountered what was here ultimately argued, and I think correctly argued, to be a scientific problem. But the recognition of precisely what scientific problem it is, what kinds of scientific developments deserve to be counted as potential solutions to such a problem, what a scientific solution to such a problem might look like. These turned out to be questions that philosophers were in many cases better able to deal with than scientists were. So a situation developed in which you had an unusually close dialogue between people who worked in philosophy departments and people who worked in physics departments going on in the course of developing what were properly understood as new scientific theories, which carried with them new empirical predictions, and so on and so forth. So there really turned out to be, at least on the purely, in terms of in terms of relations between the traditional academic disciplines, you had a collaborative project going on in which some people were involved who were paid by physics departments, and other people were involved who were paid by philosophy departments. I myself am a prime example of something like that. My PhD was in theoretical physics. I worked for several years as a professor in physics departments after I got my PhD, and then joined the philosophy department at Columbia. When I switched departments, I didn't see the character of my work as switching in any deep way or as changing in any deep way. Indeed, I used to have a rule, according to which I would write a paper, and when I was done writing it, if it had more than 2 equations in it, I would send it to a physics journal. And if it had less than 2 equations in it, I would send it to a philosophy journal. And so this kind of activity, which grew up especially around the measurement problem in quantum mechanics, but also spread out to other kinds of considerations at the conceptual foundations of physics, came to be something that people who worked in it began to refer to as foundations of physics. Some people who worked in the foundations of physics worked in physics departments. Some people who worked in the foundations of physics worked in philosophy departments. There was at the same time a more traditional sort of philosophy of physics in connection with philosophical activities that focused on things like the theory of relativity and so on and so forth, where the usual practice was to regard the physical, the sort of mathematical structure of the theory as fixed before you started to approach it. And you would look at this structure and try to get a clear picture of its logical structure, of the relations between its various logical components, and try to sort of develop a metaphysical picture that was well suited to the kind of world that the theory was describing, and so on and so forth. Something quite different than that was going on around the foundations of quantum mechanics. And philosophy of physics didn't seem to be a perfect name for what was going on there, because the kinds of activities that the philosophers ended up being involved in were the development of new scientific theories with new empirical predictions. So there has been in some of these fields a particularly close and intense kind of dialogue between people working in physics departments and people working in philosophy departments. Another thing, if you go to conferences now on these kinds of issues, it isn't easy to tell by looking at a presentation whether the person giving this presentation works in a philosophy department or works in a physics department. So it's this kind of activity that I'm referring to when I talk about foundations of physics. And this isn't anything in the nature of an official name. I'm sorry.
No, that's totally fine. But it's similar with, mathematical logicians and philosophers of math sometimes.
That's true. Yes,
you certainly couldn't tell.
That's exactly right. There's a similar kind. It's a relationship that's not very that has a lot in common with, as you say, relations between, say, logicians who work in mathematics department or who work in philosophy departments. That's right. That's right.
I recently spoke with Varzi about metaphysics, and this story I found immensely fascinating. I guess the way metaphysics got its name was Andronicus of Rhodes, if I remember correctly, was one of Aristotle's first sort of catalogers, I guess you would say.
Right.
And after he finished classifying everything, he had finished the physics, and then he had some stuff left over. And technically, or in the ancient Greek, I guess ata meta ta physica means just after the physics. So it's just
Right.
everything that's left. So the
That's, by the
the
way, I wrote a book um, in, I guess, 2015. It was published in 2015, that was called After Physics. And it was called After Physics precisely as a reference to this original Greek meaning of metaphysics. Yeah.
oh, that's really cool. And so metaphysics and physics aren't connected etymologically the way that I or many people might have assumed it was. So
Right.
we've talked a little bit about foundations. Where is the delineation then between philosophy of physics and metaphysics as you see it?
Once again, a very vague one. There is right. There isn't the kind of etymological connection that you might think there is. It's a much more, the etymology is much more arbitrary than that. But there certainly is, throughout the history of modern science, ever since Newton, um, obvious sorts of metaphysical questions that are raised by our fundamental physical theories. In the case of Newton, a lot of these questions were about the metaphysical status of space, whether or not it's a substance, and so on. So, from the very beginning of the modern era in physics, that is, you know, dating from the work of figures like Galileo and Newton and so on and so forth, um, um, there have been obvious sorts of metaphysical questions, metaphysical in the absolutely traditional sense of that word, obviously metaphysical sorts of questions in the immediate neighborhood of physics. And there's been the idea around that physics might have a lot to contribute to our metaphysics, even that physics might be, as it were, the royal road to metaphysics, the right, that what we ought to be aspiring as much as we can to be reading our metaphysics off, fairly directly off of our fundamental physics. It's been part of the discussion since the beginning that that's not as simple as you might think it is. And there were people who seemed to understand the physics very well, like Newton and Leibniz, who disagreed with one another very profoundly about what the appropriate metaphysical picture to read off of Newtonian mechanics would be. So from the very beginning, there were metaphysical disputes between substantival understandings of space in a theory like Newtonian mechanics and relationalist understandings of space in a theory like Newtonian mechanics. But I guess there's been a sense, at the very least, that that physics provides a framework of questions, or suggests a framework of questions that a lot of people felt ought to be the guiding questions of metaphysics. That what we want from metaphysics in the light of modern physics is some discussion of the status of the various things that physics seems to be referring to, or the status of the various things that physical theories seem to contain symbols of or notations for, or something like that. What is this space thing? What is this time thing as it arises in modern physics? So yes, from the very beginning, and this is a much more familiar thing, there has been there has been a very active dialogue between modern physics and metaphysics, going back at least as far as Newton and Leibniz. And many of those problems are very much alive today and very much at the center of lots of metaphysical discussions.
Okay, I'm with you entirely. You know, this is a good time. One of my good friends at Columbia, actually, she's one of Justin's students, Ronnie Rachavelpula. She wanted me to ask you a question today, actually, that's pretty relevant to what you were just talking about. She wanted me to ask you about scientific anti-realism, and that question, as I understand it, concerns what you were just talking about, whether or not we should be ontologically committed to things like electrons or quarks or fields that we can't directly observe, even though they're integral to our best scientific theories. And she was curious about how you felt on that, particularly on scientific anti-realism.
So look, there's a very well-known, very long-standing, just within the 20th century, debate about that, where you have, schools of thought like positivism and verificationism and so on and so forth, which are in some sense very anti-realist about these things that we can't directly observe. And on the other end, pretty old-fashioned, straightforward, flat-footed, scientific realist positions about these things. The other interesting thing that happened in the 20th century on the scientific end, which got tangled up with this, positivist critiques of realism are pretty straightforward, traditional philosophical kinds of critiques. What happened in the beginning of the 20th century with the advent of quantum mechanics is that it was thought that what was going on in quantum mechanics presented an entirely new and unprecedented kind of critique of realism, not a critique coming from traditional philosophical sorts of considerations, but a critique coming from, as it were, inside of physics itself. Okay, it was like this moment in a horror movie when the telephone operator tells you that the call is coming from inside the house. Okay, there's the founders of quantum mechanics, people like Bohr and Heisenberg and Born and so on, basically announced in what sounds today like a really paradoxical and confusing position, but basically announced that the results of certain experiments that were designed to probe the interior structure of atoms and so on and so forth, the empirical results of these experiments were incompatible with any realist picture of what was going on in the interiors of atoms. Okay, like I say, there's a long history of distinctively philosophical sorts of critiques of realism. The interesting thing about what happened in physics in the 20th century was that there was supposed to be this radically different and unprecedented kind of critique of realism coming from the physics itself. There were arguments from people like Bohr and Heisenberg that depended specifically on, empirical experimental results that were coming in at the time, that any attempt to subsume these experimental results or to explain these experimental results within the context of or building on some traditional flat-footed, realistic, mechanical picture of what was going on, of what was really going on in the interiors of atoms, was, so they said, for all sorts of reasons, going to collapse into paradox. Okay? And they thought that what's usually thought of in philosophy is what you might call a militantly instrumentalist approach to science was the only available one. Okay. Science now needed to be understood. And once again, this kind of position had previously been the upshot of all sorts of distinctively philosophical critiques of realism. Okay. This was a new sort of critique of realism, and as it were, empirical critique of realism. They thought that the only way of understanding what physics was doing that was going to survive what had recently been discovered in these experiments was a radically instrumental understanding of what physics is doing. That is, an understanding of what physics is doing as nothing over and above coming up with procedures for predicting the outcomes of future experiments, okay? And any attempt to, as it were, penetrate more deeply beneath the surface of the experimental data than that was, as I said, going to collapse into incoherence and paradox, okay? This was accompanied by a tremendous amount of philosophical excitement. Bohr, it's known, had in the back of his mind all sorts of philosophical figures like Hegel, like Kierkegaard, so on and so forth. And it was thought around the middle of the 20th century that, for example, all kinds of other radical conclusions might be forced on you. Perhaps you could come up with a realist understanding of quantum mechanics, but the price you were going to have to pay was going to be in terms of modifications to classical logic. Okay, so that attempts at a realist understanding of quantum mechanics were made in the middle years of the 20th century. But like I say, it was thought that the only way to come to grips with the kinds of arguments that Bohr and Heisenberg had made was to sacrifice the distributive axiom of classical logic. That is, to deny that A and B or C entailed A and B or A and C. Good. In my view, and I think in the view of most of the people who study foundations of quantum mechanics nowadays, all of this was mistaken. All of this was misguided. We now do have old-fashioned, flat-footed, realistic accounts of what's going on, for example, in the interiors of atoms. What we needed in order to achieve accounts like this was some solution to the measurement problem, some genuinely old-fashioned, non-verbal, non-distinctly philosophical, scientific solution to the measurement problem, of the kind that philosophers have been urging on physicists, as I was talking about before, for the past 50 years. So looking back on all this now, there was this very novel, very exciting purported challenge to realism coming from within empirical science itself. Okay, and what I mean by from within empirical scientists, from within empirical science, is not just that it was practicing empirical scientists who were who were propounding this anti-realism, but that it was their position that this kind of anti-realism was forced on us by experimental data. Okay. Anyway, looking back on this from 100 years later, a lot of it looks very silly. A lot of it looks like very premature jumping to conclusions. But that's the sort of novel thing that happened to the conversation about realism in physics in the 20th century. That having now been taken care of, yes, there are still left around all of these old-fashioned, distinctively philosophical critiques of realism, the kind of critiques that lead to idealism, the kind of critiques that lead to phenomenalism or to positivism or to verificationism, or something like that. All of those are still very much around. I don't have if the question is, what's my position on these old philosophical discussions about realism? My gut instincts are realist. Those are coming from physics. But I mean, if the question is, do I have a good refutation of idealism, or do I have a good refutation of skepticism, or something like that? No, I don't have a refutation of skepticism. I don't have a refutation of idealism. I think, interestingly enough, and this is part and parcel of this same development of philosophers insisting that the measurement problem was not a philosophical problem, it's a scientific problem. There's some sense in which, in a nutshell, what happened in the 20th century, in 20th century physics, in connection with these problems, was there was this moment of thinking that the progress of science itself had suddenly injected itself into this old debate about realism, that it had injected itself decisively on the side of anti-realist positions. And it took about a century to clear that up, okay? And to conclude in what sounds like an anticlimactic way, but was actually a profoundly interesting way, that nothing of the sort had happened. Okay, that the realism anti-realism debate as a debate within philosophy proper was in exactly the same place that it had always been. Okay, that realist understandings of what we were discovering in physics were no less available after quantum mechanics than they were before quantum mechanics, but the extent to which they are available, the extent to which they are viable, is precisely the old-fashioned, distinctively philosophical kind of question about which discussions have been going on for a long time.
It's funny to me that before you were here, you said you hoped you were going to be on today, and I think you're very much on your game. But now I think I have a much better understanding of this continuum that I hadn't really known existed before we started talking. And having this knowledge makes me understand why I was having so much trouble figuring out just where to start a conversation on time, because I'm sure that each of these 4 distinct places and all along the continuum, there are very substantively different questions about time to be asking. So I'll give you a couple of options.
Sure.
You mentioned that one of the initial obvious questions in philosophy of physics, or somewhere blended with that in metaphysics, is whether space is a substance. And I
Right.
think that is really a natural starting point for talking about time as well, simply because if we look at our everyday language, we talk about counting seconds. What time is it? It's past the time. We think about think about whether or not we can freeze time. So time very much seems like an object. And I thought, okay, maybe that would be a great place to start. But I also thought that, or I'm pretty sure I read that you're teaching a course on the arrow of time right
Right.
now at
That's right.
Columbia. So I thought maybe we could talk about what you talk about on the first day of class, or
Sure.
this issue of whether or not is time an object, or does it
Sure.
reduce to something else?
Um, um, so here's what we talk about on the first day of that course. Um, um, and this again, the way I'm going to describe it now, and I think the way it's appropriately understood, arises as a tension within physics itself, not between physical ways of scientific ways of thinking and philosophical ways of thinking, but it arises as a tension if you're doing it properly within the scientific, within physics itself. The tension arises as follows. Imagine that you're watching a film of two billiard balls colliding with one another somewhere in intergalactic space. So you don't see anything in the film except these two billiard balls. Okay. And what you see in the film is something like this. This billiard ball is initially at rest in the middle of the frame. Another billiard ball comes in from one side of the frame, hits this one, stops, and this one goes off and exits the frame from the other side. Imagine that you're shown the same film in reverse. What you're going to see is something like this. Okay. And what I'd like you to reflect on is that the process you see when the film is shown in reverse, namely this one, is every bit as much in accord with all of the intuitions that you have about how billiard balls behave when they're colliding as the film, as what you see when you're shown the film in the correct direction. Okay. That is, if you were shown such a film and asked to guess, and you were asked to guess whether you were being shown the film forwards or in reverse, the various intuitions you have about how billiard balls behave when they collide would be of no help in guessing whether you're being shown the film forwards or backwards. Moreover, one can precify this a bit. It turns out that that the laws governing things like behaviors between billiard balls have a mathematical property that physicists refer to as time reversal symmetry or time reversal invariance. Okay, which means that if a certain process is a solution to the equations of motion that come with the laws describing collisions between billiard balls. That is, if a certain process is in accord with the laws that we've developed describing behaviors between billiard balls, then necessarily the same process going in reverse, that is what you would see if you watch the film in reverse, is another process that is also in accord with those laws. Okay, that these laws have a certain mathematical feature referred to as invariance under time reversal, which guarantees that for any process that's in accord with those laws, the same process going backwards is in accord with those laws as well, so that it follows not just from your intuitions about what billiard balls do when they behave, but from what we actually take to be the complete and exact laws describing how billiard balls behave when they collide. That that no amount of information about what these billiard balls are doing would allow you to guess reliably whether you're being shown the film forwards or in reverse. We talk about that in physics, as I said, by saying that the laws governing the collisions between billiard balls are invariant under time reversal. And here's the surprise. It turns out that insofar as we can tell at the moment, insofar as has emerged from our detailed laboratory experience together with our experience of theorizing about what we see in the laboratory, all the evidence we have to date is that the complete fundamental laws of physics appear to be invariant under time reversal. Okay. Now, of course, we don't know yet what the complete fundamental laws of physics are. Physics isn't done yet. But here's something that's true and strikingly true. Every single proposal for the fundamental laws of physics, starting with Newton, going through the 19th century developments of electric and magnetic fields, and so on and so forth, into the 20th century theory of relativity, quantum mechanics, so on and so forth. All of the proposals for a fundamental theory of physics, okay, that have been seriously entertained by anybody since the scientific revolution of the 17th century, have shared this mathematical feature of invariance under time reversal. This is a really striking thing, because over that time, almost everything else about the fundamental laws has changed or has been thrown up in the air. What the actual structure of space and time are, whether these laws are deterministic or indeterministic, so on and so forth. All of that has been called into question. All of that has been at risk and at stake in the stuff that's happened in physics between the 17th century and now. Something that has remained absolutely constant is that all of the proposals that have been taken seriously, that have really been entertained by anybody as serious proposals for the structure of the fundamental physical laws, have all been symmetric under time reversal. Good. So once again, we don't know yet what the final laws of physics are going to turn out to be, but there's some sense in which all of the testimony we have so far from our combined empirical and theoretical experience testifies very strongly in favor of the idea that the fundamental microscopic laws are going to turn out to be time reversal symmetric. Good. What produces the tension is the very obvious observation that if you consider films of other physical processes, not billiard balls colliding in space, but of people walking down the street or eating a meal or aging in time-lapse photography or so on and so forth, you can very easily tell by being shown the film whether you're watching it forwards or backwards. Okay.
Right.
Nature, our everyday macroscopic experience of the world is absolutely swarming with processes everywhere you look, which have a pronounced time directedness about them. Okay. The world is just full of processes everywhere you look, which don't ever seem to happen in reverse. okay? Unlike the case of the billiard balls, okay? So there is this tension, and mind you, this is a tension completely internal to our scientific picture of the world. We don't have to raise any philosophical considerations to get at what the tension is. We have, on the one hand, our microscopic laboratory experience of the world, which seems to point very strongly in terms of comprehensive fundamental laws, which are completely symmetric under time reversal. Okay. And we have, on the other hand, another piece of our experience of the world, our everyday macroscopic experience of the world, which seems to be swarming with processes that are not time reversal symmetric. Okay. And there is a scientific question of how to put these two domains of our experience together. Okay, of what we should make of this tension sitting right at the heart of the scientific project of investigating the fundamental physical laws of the world. So that's more or less the content of the first class in this course. There is this tension between what we seem to learn from our controlled laboratory microscopic empirical experience of the world and what we seem to learn from our everyday macroscopic experience of being in the world. And what we want to do in this course and what various branches of physics and the foundations of physics and the philosophy of physics have been struggling with over the past 100 years. A big problem that they've been struggling with over the past 100 years is what to make of this tension, what to do with this tension, how to develop a comprehensive scientific picture of the world, which somehow takes into account both this microscopic laboratory experience and this macroscopic everyday experience of the absence in one case or the presence in the other of a pronounced, vivid directedness, time directedness of ordinary physical processes. By the way, let me just expand the tension a little further. It's not just that there are physical processes, people walking down the street, ice melting in a warm room instead of freezing in a warm room, blah, blah, blah. It's not just that there are all these everyday physical processes that seem to have a time directedness about them. There are at least two other levels which one wants to worry about as well. There is what you might call an asymmetry of epistemic access between the past and the future. The kind of epistemic access we have to the past is very different from the kind of epistemic access we have to the future, and the procedures we have for coming to know things about the past seem very, very different from the procedures we have for coming to know things about the future. And once again, all we're talking about here at the end of the day are physical processes, okay? Why is it that there can be such a thing as a photograph of something that happened yesterday, and there isn't any such thing as a photograph of something that happens tomorrow? This is, at the end of the day, only a question about correlations between the positions of atoms in a photographic emulsion, okay, and the positions of various other atoms out there in the world, of which this emulsion is a photograph, as it were, okay? Why is it that there can be those kind of, why is it that the physical photograph always has to be later in time than the event that it's a photograph of, okay? If you take seriously these microscopic discoveries that suggest that the fundamental physical laws don't have any time direction in them in this way, it's profoundly mysterious also why there should be these asymmetries of epistemic access. Okay, why records or memories of events should come temporally after events and not temporally before them. Okay, and similarly, on a third level, and this is a more metaphysical level, but one that's how shall I put it? That a lot of pressure is being put on from the physics. We make our way about in the world in a very practical sense with the conviction that by acting now, we can potentially affect the future, but not the past. Okay. Once again, if the fundamental laws of physics don't seem to make any distinction of that kind, why should that be true? Okay. What's going on there? Okay. So there are all these levels. We talked about three of them here. The level of what you might call ordinary physical processes. We see smoke spreading in a room. If we see a movie where the smoke all collects back into the cigarette, we know we're watching the movie backwards. Okay. So there are on the level of ordinary physical processes, on the level of epistemic relations, on the level of causal relations, there seem to be profound asymmetries between past and future. There seems to be a profound time directedness in the way that the world works. Okay. Whereas on the level of our microscopic laboratory experience and the theorizing that that has produced, there doesn't seem to be any such asymmetry at all. Okay. What are we supposed to do with that tension? So that's the first day of this class.
Yeah. Naturally, my instinct is to say, yeah, tell me the answer. I want to know the answer.
Right.
But that's what you I'm sure go into for the duration of the course, and the questions still aren't solved.
But let me tell but here again I can say a little bit. Okay, here again there are going to be two roads facing you, and there's going to be a decision to make about which of these roads you want to take. You might think that how shall I put it? You might think that the right place to address questions about, say, asymmetries of epistemic access or asymmetries of causation is someplace logically prior to physics, on the level of metaphysics or on the level of linguistic analysis or phenomenological analysis, or something like that. That is, there's going to be a strong temptation to say, what do you mean, why can't I remember the future? Because the future hasn't happened yet. Okay.
Yeah.
You know, or why can't I change the past? Because the past is already finished. Okay. There's nothing you can do about it. Okay. And if you were to take this seriously, you might propose a sort of metaphysics, or even on the level of logic. I take it Aristotle thought there was a sort of logical difference between the past and the future, that there wasn't now a fact about who's going to win the naval battle tomorrow. Okay. But there is now a fact about who won the naval battle yesterday. Okay. Good. So you might say the place to look for an understanding of at least the higher levels of these differences is someplace outside of the jurisdiction of physics, logically prior to physics, okay, at the level of logical distinctions or deep metaphysical distinctions or something like that. Or you might say, no, what I think I would like in terms of an explanation of all of these distinctions, the time-directedness of ordinary physical processes, the time-directedness of our epistemic access, the time-directedness of causal relations. What I'm looking for in all these cases, if I can have it, is a scientific, mechanical account, okay, of how these asymmetries come up, not a distinctively philosophical account, okay? And or you could take a very different, you could take a very different direction and see this, especially in the causal case and maybe in the mnemonic. You know, you might want to say, no, it's analytic to the very notion of a record or a memory, that it's a record of the past, okay? Mm-hmm. And then you would need a metaphysics that comes from the word go with a distinction between past and future built into it, whereas the physics doesn't seem to have that, okay? So anyway, there are several directions in which you could go. There's a philosophical question, and this very much parallels what we were saying about the measurement problem before. You might say there's the following kind of dialectic. An approach you could take, just as with the measurement problem, is to insist that this is something for physics to answer. Okay, that say in the case of epistemic access, what you mean by having epistemic access to X is the possibility of establishing a correlation between physical stuff that's going on inside of your skull and X, okay? That's what it is for you to have epistemic access to the facts about X. Okay, and if that's what it is to have epistemic access, it ought to be science that determines what we have epistemic access to and what we don't have epistemic access to, and why our epistemic access to things in the future is different from our epistemic access to things in the past, and so on and so forth. Good. So there can be a similar dialectic going on here of people with a certain level of philosophical sophistication insisting that what's to be learned from philosophy here is that this should be treated as a scientific problem. Okay. Those, I guess, those are also the inclinations that I have in response to a problem like this. Right.
So let me ask you then about that direction first in particular. So you mentioned that this time reversal asymmetry has been inherent to all of our physics since Newton.
You mean least. Time reversal symmetry, not asymmetry.
Yeah. Right. Yes, precisely, right. Symmetry. I'm sorry.
The asymmetry is what comes up in our everyday experience.
Right. And asymmetry is what I want and what we want. And so what I was wondering then is if contemporary theoretical physics are trying to somehow bake this asymmetry in, like yes. in string theory or quantum gravity.
Here's the in very crude terms, here's the general approach. First of all, just as a logical matter, if the complete set of physical laws is indeed time reversal symmetric, you're never going to get any time reversal asymmetry out of it, okay? No asymmetry going in, no asymmetry coming out, okay? So you've got a very simple argument. If we're going to understand the various systematic time asymmetries that we encounter, okay, that's going to require some modification of what we take to be the fundamental laws of physics. Okay, that's going to require some move that says, yeah, there must be another law which for some reason we haven't noticed or hasn't been pushed in our faces by our microscopic laboratory experience, but must necessarily be there. Okay. And one popular way of thinking about addressing this problem is to add a law that stipulates something about the initial conditions of the universe. Okay. What the initial conditions of the universe actually were. I mean, to take a ridiculously simple example, if we had a law that the initial conditions of billiard balls are always like this and never like this, okay, then we would be able to tell if we were watching the movie forwards or backwards. Our experience informs us that there are no laws like that, that we see this kind of process just as often as we see this kind of process. Okay. But the question is, could you imagine laws that we could impose that constrain the initial conditions of the universe, okay, and that are hopefully relatively simple and so on, that would somehow explain in a unified way. So the total set of laws would be a combination of two kinds of things. You'd have these dynamical laws, which don't have any time asymmetry inherent in them. And you combine those with other laws constraining what physicists call the possible boundary conditions of the world, okay? You combine those dynamical laws with some other less familiar kinds of laws saying, on one temporal end or another, there must have been a state like this, okay? And the question is, if we can come up with a way of filling in the like this blank, okay, which is relatively simple, and which, if we added it to the dynamical laws, would in a fairly unified way, at least arguably, explain this temporal directedness of ordinary physical processes, also this temporal asymmetry of epistemic access, also this temporal asymmetry of causal relations, and so on and so forth. If there were some simple postulate we could add, and people do focus on this postulate being some postulate about the conditions that the universe satisfies at one temporal end or the other, if you could find a simple such postulate, that might be a satisfying scientific solution to this problem. And there's a good deal of reason to believe that there is a simple way of specifying what you need in terms of a quantity that comes up in thermodynamics called entropy. I won't go into a big spiel about what entropy means, but it is thought that if you add, well, I don't want to say more than we know. There's a lot of speculation in the direction that it might do all these jobs in a sort of breathtakingly simple and concise way if we simply added to the dynamical laws we know about a stipulation to the effect that at one end or the other of the temporal axis, the universe has a physical state whose entropy value is very low. Okay. To make this make any sense, to make it plausible that it even begins to address the task of explaining these asymmetries would take a semester, which is what I'm doing in this course that you just talked about. But yes, that would be an example of a kind of militantly naturalist approach to this problem. Okay, we don't need, it's not going to involve any kind of linguistic or logical or metaphysical analysis of the difference between past and future. Okay, the claim would be that there is no logical or metaphysical distinction between past and future. The distinction entirely has to do with the equations of motion and this constraint on boundary conditions.
So before we go to the non-naturalist side of things,
right,
you said that we can do this without presupposing too much about past and future, and I'm wondering, well, it strikes me that a big question about time is being presupposed by this strategy, and it is smuggled in by presupposing that the universe has an initial state, because a big question about time is whether or not it has a beginning.
Right.
Or
right. Oh, I see. Okay. So there are two distinct ways in which you might think something is being smuggled in. One is whether time has a beginning or an end. Okay. The other is, even if it did have a beginning, even if the duration of time were finite, in virtue of what is it that we're calling one of those ends the initial end?
Okay, yeah, that's not what I was referring to, but that is, I see another.
Good. Huh. So we can take both of those. We can take both of those questions separately. The first question, that is, would this kind of reasoning apply even if the temporal dimension is infinite in extent? Yes, but in slightly different ways. Then what you would be imposing is some condition at some point, okay, in this infinite continuum, call it time zero, okay, but that's not meant to imply that there are no time, there are negative valued times before that, okay. Impose this low entropy boundary condition, or this low entropy condition at some arbitrary time, okay. Then the claim is, on either side of this boundary condition, okay, you're gonna have physical behaviors of the world where people on one side of this boundary condition are going to find that they only have memories and records of those times in between where they are and the moment of that low entropy condition. Okay. And people on the other side of this boundary condition are going to find that they only have memories and records of what went on at times in between where they are and that low entropy boundary condition. But those are going to be, when these two different, separated civilizations talk about the past, point towards the past, they're going to be pointing in opposite temporal directions. Okay. Maybe I should draw a picture of this. Hold on.
No problem.
So you have some temporal line like this. That's T. Okay. Suppose you say that at a certain point here, the universe has a very low entropy condition, okay? That low entropy condition will be the condition that astrophysicists refer to as the Big Bang, okay? What they call the origin of the universe, not necessarily the origin of the universe in the maximally grand sense, but as far back as our observational procedures can take us, and so on and so forth. Good. So you might have whole civilizations living around here, okay, they will refer to the past as the interval between this and where they are now. And they will
Okay.
refer to the past direction as this direction. Okay.
Yep.
Might also have civilizations on this side. Okay. They can't communicate with each other. All records get wiped out when you go through this Big Bang. Okay. It, as it were, destroys everything. These people will find that they can remember here stuff between there and there, and they'll refer to the past as this direction
Okay.
from where
So
they
are
are.
we thinking of it as directional, it going in both directions?
It's always going towards this low entropy moment,
Okay.
okay, from wherever you are. That's what you mean by the past, okay?
Okay.
And it's going to be on this side of it. Smoke is going to spread as you go in this temporal direction. On this side of it, smoke is going to spread as you go in
Okay.
that.
Yeah, that answers my question.
Okay. So that answers the question about the potential infinity. Okay. Similarly, what if time is finite? Okay. What do you mean by saying you impose the low entropy condition at the beginning as opposed to at the end? Okay. The answer to that question is going to be the same one. No, there's no such thing as you impose it at one end. Okay. And whichever end you impose it on comes to define what we call the past direction. The
I see.
direction in which we remember things, the direction away from which smoke spreads, blah, blah, blah. Okay. So that's
Hmm.
roughly how that's going to work. So yes, it's adaptable. It's perfectly adaptable to situations in which the the total temporal in which the temporal axis is infinite, and also there isn't the notion of initial as opposed to final being smuggled in there. You impose that boundary condition at either end, and that's what defines for you past and future.
Now,
I mean, I feel incredibly corrupt saying all of this because this is stuff that I would squeeze in over the course of an entire semester. And even over the course of an entire semester, it's a bit of a squeeze. So um, I'm used to demanding of myself that I explain this in a much, much more understandable way than I'm explaining it here. And as I said, this makes me feel incredibly corrupt. To
no,
talk.
well, I think I'm following for the most part. And one question that I have now goes back in time to when I gave you this pair of choices between talking about the first day of class or talking about whether or not time is an object
Right.
or it reduces in some way to something else. And in this scientific direction that we talk about, the naturalistic way, we seem to be reducing time to, I don't know if you want to call it laws, but theorizing in some way that doesn't take
Yes,
time
no,
as an
actually, I
object.
think reducing it to laws is a very relevant thing. Let me actually say a few words about that.
Please.
Um, um, talk about a distinction that seems to be even lower down, logically speaking, than the ones we've been talking about here. So here we've been talking about, as it were, naturalizing the distinction between the forward time direction and the backward time direction. It's possible to go further down than that and sort of naturalize one conception of what it is that distinguishes the time axis from the spatial axes, okay? Or what it is that gives rise to the category of the temporal in the first place, okay? So you can think of something like this. think of the world, think of the entirety of the world as some four-dimensional collection of points, okay? At each of these points, there is some specified set of physical properties. At each of these points, you can say, is there or is there not a particle there? Is there or is there not an electric field of a certain strength there? Blah, blah, blah. Okay, good. So we have this, what physicists refer to as a decorated four-dimensional manifold of points. What I mean by decorated is supplemented with physical properties, with physical descriptions of what's going on at each of those points, okay? We speak of the four-dimensional manifold as decorated with physical properties, or if you have a different attitude towards life, you could describe it as befouled by physical properties, or whatever. Anyway, good. It might be the case, it might or it might not be the case, and there's nothing necessary here. It might be the case that for certain decorations of this four-dimensional manifold, okay, you can find ways of slicing the manifold up into three-dimensional submanifolds, such that there are very simple rules that can tell you, given the way that one of those slices is decorated, how other slices will be decorated. For example, how neighboring slices will be decorated. Okay, that is, there are simple rules that tell you, given where there are particles and what kinds of particles there are and so on along some of these slices, along one of these slices, there'll be a simple rule to get you from the physical description at each point on one of these slices to the physical description at each point on another of these slices, okay? Consider, for example, a world like ours, okay? Here are two ways of slicing up that world into three-dimensional subspaces. One slice is the slice that goes across the whole universe at 3 p.m. on a certain date, okay? And the other is the slice that goes across the whole universe at 4 p.m. on the same date, okay? Here's a different orthogonal way of slicing it up. The slice that goes from t equals plus infinity to t equals minus infinity right through the location of the Empire State Building, okay? That is a slice that's located by specifying a particular position in space, okay? And another slice that goes through some point in Los Angeles from t equals minus infinity to t equals plus infinity. Good. Here's what I'd like you to notice. Consider the slice at 3 o'clock and 4 o'clock. There'll be lots of really simple relations between the slice at 3 o'clock and the slice at 4 o'clock. For example, they'll both contain the same total number of particles, okay? It turns out also that they'll both contain the same total energy and the same total momentum.
Okay.
Consider the slice through New York from t equals minus infinity and through to t equals plus infinity, and the slice through Los Angeles. There are no such simple relations between those slices, okay? It might be that there are way more particles in New York, more or less forever, than there are in Los Angeles. It's not true that for every particle that ever shows up in New York, it has to show up sometime in Los Angeles. There's no such regularity in our world.
This is really
But there is a regularity of the form, for every particle that shows up at 3 p.m., it has to show up somewhere at 4 p.m., okay? Good. So it turns out that the world just is. Nothing constrained it to be that way, but it is this assignment of physical properties to points in this four-dimensional continuum. It might be with certain such decorations, okay, that you can find simple rules that link one slice to another. Okay, good. If there are, you call those two slices different times, different temporal instants, okay? And you call the rules that link them dynamical laws, like the dynamical law of conservation of total number of particles, the dynamical law of conservation of energy, the dynamical law of conservation of momentum, so on and so forth. Okay. And what you mean by the temporal axis, and all you mean by the temporal axis, and all you mean by the distinction between the temporal axis and the spatial axis, okay, is that the temporal axis is the axis where there turn out to be simple rules linking the situations on different parallel slices. And the spatial axis is the axis where they turn out not to be simple rules, linking the physical situations on the parallel slices. And that's it, okay? Even the distinction between space and time itself on a view like this is a fully naturalized distinction. It's not a metaphysical distinction at all, okay? All of these points are metaphysically on a par with one another. All of these slicings are metaphysically on a par with one another, okay? They're only not on a par with one another physically, okay? They're not on a par with one another in terms of the way the distribution of physical properties over one slice is related to the distribution of physical properties over another slice. But their character as physical properties, there are no metaphysical distinctions there, okay? So one can carry this mania for naturalization still farther, okay? This goes back, this proposal about a way to naturalize the distinction between space and time is a proposal that goes back at least to the 1950s, to a beautiful paper, God, now I'm going to forget his name, called The Myth of Passage by D.C. Williams. That's his name. A really, a paper I'd recommend to everybody. It's called The Myth of Passage by D.C. Williams. Really, really beautiful paper. He just mentions this proposal very modestly and very quickly in the last two paragraphs or so of the paper. It's a train of thought which has been developed a good deal more since then, and elaborated a good deal more since then. But it's a very beautiful idea, and it's a striking example of how far one can, of the extent to which, if one is in the mood, one can drag what feel initially like metaphysical questions into the domain of the scientific.
So I'd like to go back a few minutes to the time slices,
right,
and the space slices, because I had a flurry of thoughts there. And one is, I might be incorrect here, but it strikes me, based on my limited understanding of relativity, that it's an illegitimate move to suggest that there can be slices drawn. So there's no absolute simultaneity. So to say that there's like a slice now that is now across the universe, we just can't say that.
That's absolutely right. But
Okay.
that's how shall I put it? What I'm talking about here
Is
that's right, is prior to that, and is absolutely consistent with that. That is, what happens in relativistic theories is that there turn out to be a bunch of different ways of slicing the manifold up, such that there are laws linking parallel slices. Okay. One of those ways of slicing it up corresponds to simultaneities for observer A. Okay. Another way of slicing it up will correspond to simultaneities for observer B. There is no absolute simultaneity. What that means is there are many different ways you could slice it up such that you'll get these rules, but there still are ways of slicing it up so that you won't get these rules, okay? So that you won't get these links. These will be, that is, relativity says there's no absolute fact about simultaneity, okay? But there are events, so-called time-like related events, that are not simultaneous from any observer's point of view, okay? That is, that are absolutely non-simultaneous, okay? That corresponds to the slices through New York and the slices through Los Angeles. So yes, to refine this a little bit in order to take account of the difference between, say, Newtonian mechanics and relativity, you might say that it's characteristic of Newtonian mechanics, where there's an absolute simultaneity, that there's only one way of doing this slicing so that you get these simple rules. In a theory like special relativity, where there's no absolute simultaneity, what the situation we have is that there are many ways of doing this slicing so that you get these rules. All of those are qualified to count as times, okay, by this naturalized definition of what a time is.
Okay, so I'm glad to hear that they're compatible, yet then I also wonder whether there might be a larger issue, or maybe it's just another question whose answer is being presupposed, and that's whether or not it's even admissible to talk about there being this four-dimensional manifold at all, because that seems to presuppose that the past, the future, and the present are all somehow equally real, and it is not just
Yes,
the present that exists.
absolutely
And
right.
Before you continue,
yeah.
before you answer that question, and I think this goes back also to the scientific anti-realism, because in a way, even if we don't want to admit the reality of the four-dimensional manifold, we still might make use of this as an instrumentally to answer certain questions. But okay,
so
that's all.
So let me say a couple of things. This four-dimensional manifold there might be not there might be, there will surely be ways of distributing physical properties over this manifold such that there isn't any way of slicing things up so that there's always a simple rule linking parallel slices, okay? Indeed, if you just pick a distribution of properties at random, okay, the overwhelming majority of those choices are not gonna feature any way of slicing things up so that you get these simple rules, okay? You'll just have a chaotic, a chaotic distribution of properties over this four-dimensional manifold, okay? So in universes like that, we would say these universes don't have any temporal nature at all, okay? There's just a four-dimensional distribution of properties, okay? So when you say dealing with this four-dimensional manifold is taking it for granted that the past and future both exist, well, yes and no, okay? It's taking it, because given a four-dimensional manifold with an arbitrary distribution, temporal terms may not have any application at all, okay? They're
Yeah,
only going to
I
have
can
an
see that.
application in the event that the pattern turns out to be such that you can find a way of slicing it up that's gonna give you these simple rules. Okay, so I guess I
Sure.
would agree to the
Yeah.
following conditional statement. Talking about this four-dimensional manifold is taking it for granted that if the thing turns out to be temporal, okay, yes, then assuming the four-dimensional manifold is going to be tantamount to assuming that past, present, and future all exist. That's right. Okay. But in most of these manifolds, temporal language isn't going to even make any sense at all. Okay. It's just this four-dimensional arrangement of physical properties. Okay. That's all it is. So I agree with you. But on the other hand, if you're thinking of it this way, that seems like a funny thing to complain about. Okay.
Mm-hmm.
What you would say to the guy is, no, I'm not assuming past, present, and future exist. Past, present, and future are just ways of talking about this four-dimensional chunk, this four-dimensional arrangement of physical properties. Okay. You're right. I am taking as given this four-dimensional arrangement of physical properties. I'm taking it for granted that that every proposition of the form, this point has this physical property is true or false. Okay, that's true. Okay, that will amount in cases that turn out to be temporal. Okay, to assuming that statements about who wins the naval battle tomorrow are timelessly true or false. Yes, in a way that, say, Aristotle thought was not the case. Right. That's right. So we're guilty on that count, but not quite as guilty as you were implying, because the form of the assumption is not an assumption about past and future existing, because we're not even assuming there is any such language as past and future. If there is a language of past and future, then assuming this chunk is tantamount to assuming that past and future exist. But you see, given the fundamental metaphysical picture here, that's a funny thing to get all worked up about. Okay.
Mm-hmm.
The world is just this four-dimensional chunk. Okay. Distinguishing spatial axes from temporal axes comes much further downstream.
Let me ask you a very unrelated question, because it's something I've been thinking about since our last discussion with Justin.
Uh-huh.
He wanted to talk a lot about math and logic and morality. And in the context of that discussion, you mentioned that you identify as an expressivist. And okay, if that's not what you said, I don't want to put words into your mouth.
No.
But
I don't. So I probably said something. I mean, I tend to be um, if I said the kind of thing I usually say, I probably would have prefaced it by saying something like, "This is above my pay grade."
yes,
Uh,
that is probably the phrase you used.
and so I would repeat that here. Here's what I would say.
Well, maybe you could say what expressivism is very quickly first.
Sure. Expressivism, as I understand it, is the position that claims like murder is wrong, okay, are not propositions, are not to be understood as propositions which are either true or false. To understand them as propositions which are true or false, I guess, is to be a moral realist. That's what they call moral realism. Expressivism is a denial that they're true or false, even a denial that they're true or false as expressions of beliefs of mine or something like that. Okay, that is, murder is wrong is also not to be understood as the claim that the speaker believes that murder is wrong, okay? Because then if it's a belief that seems to get you back in the position where it seems to be a relation between the believer and some proposition,
which may be true or false.
Right. So that's not going to get you out of the claim that it's a proposition. Expressivism, I take it, is the denial that it's a proposition, and it's supposed to be that kind of an utterance, okay, is supposed to be understood more by analogy to utterances like ow, okay, or when somebody stubs their toe, or something like that. Ow
boo
is not
is what I often hear.
Say it again. Or boo. Exactly. Boo. Right.
Yeah.
Murder. Boo. Right. Or something like that. Good. These are not to be understood as propositions. Okay. These are to be understood as these other kinds of utterances, and the role of these utterances in our discourse has to do with trying to get people to behave in certain ways, or something like that. Okay. I'm not an expressivist to the extent that so let me say a couple of things. As you can tell from this conversation, I'm really interested in a sort of militantly naturalist sort of project generally, okay? If you ask me, am I interested in this project because I believe naturalism is true, okay, I'm not sure I would know what to say about that. I believe, Sidney Morgenbesser, who was a philosopher at Columbia many years ago, who I very much loved and admired, and who there are all kinds of fantastic stories about that I won't start to drag you through here. But Sidney Morgenbesser used to make a nice distinction between what he called believing that and believing in. Okay. I wouldn't say that that I believe that naturalism is true. How the fuck would I know? Okay. What I would say is that I believe in naturalism as a project, okay, by which I mean it's a really interesting intellectual project. That the project of naturalism has so far taken us much farther than you might have initially dreamed it possibly could. Okay, say even elucidating the difference between things that initially looked obviously metaphysical, like the distinction between past and future, or the distinction between space and time, as we've been talking about here. It turns out that you can push a naturalist kind of approach to try to make those kinds of distinctions for you. God knows how far you can push this. The sense in which I'm naturalist is not that I believe that a certain proposition called naturalism is true, but that I believe that this project of seeing how far one can push naturalism before it falls apart, okay, is a really interesting project, is a really interesting thing to do with one's mind, okay? I take it that the scientific project, the naturalist project, you often hear people say in the media and so on, the scientific project involves no less a leap of faith than the religious project or anything else. You're assuming that there are going to turn out to be a complete set of laws. This seems to me the exact opposite of what's true. Okay. The question that the scientific project is aimed at settling above all others is the question of whether you can push this naturalistic project all the way, or whether there's some point at which it collapses. Okay. That's the question that's being investigated by the scientific project. Okay. Over and above all more specific questions, all more local questions. It's precisely the question of whether the scientific project, whether the naturalist project at some point collapses. This is what was at stake in the debate about quantum mechanics that we were talking about an hour and a half ago. Okay. The claim of the founders of quantum mechanics was that the naturalistic project had collapsed not for external philosophical reasons, but as it were, under its own weight. Okay, that the sort of internal, to use sort of Marxist terminology, the internal contradictions inherent in the naturalist project had overwhelmed it from the inside and caused it to collapse. Okay, and what was exciting about the past 50 years of work on the measurement problem was that these pronouncements turned out to be premature. Okay, it turned out that the naturalistic project survived that. Okay, and the naturalistic project turns out to be this kind of energizer bunny. Okay, you have all these people coming up and smashing it, and it keeps going on. Okay, and there is this interesting question: when is it going to run out? When is it going to collapse? Is it going to collapse? Is there some kind of wall it's going to hit? The discovery of such walls has been announced again and again, and always prematurely. Okay? Like Mark Twain said, the reports of my death have been greatly exaggerated. Okay? This is what interests me. So you say, are you a naturalist? If that means, if that
well, I
means,
asked if you were an expressivist.
Right. Okay, good.
Okay.
So here's the sense in which I'm an expressivist. What I'm told by people who've thought about this much more than I have is that the best spiel we have about ethics from a naturalistic point of view is probably an expressivist one. Okay. I haven't thought about it very much. Okay. But I see the idea. I see how it's naturalist. Okay, yeah, I'll go with that. I'm certainly interested in some kind of naturalistic attitude towards these things because I'm interested in naturalism as a project. Okay. Naturalism isn't a proposition that I believe to be true. I think that's like I say, an open question, the open question of the scientific project. But I'm interested in naturalism as a project. Okay. And if you ask me in the context, and the sense in which I'm an emotivist is the following. If somebody comes to me and says, isn't your naturalistic project refuted by ethics? I'll say, well, no, not obviously. You might take an emotivist view towards ethics. That's the extent to which I'm an emotivist.
Okay. Well, where I was going, and I will leave it at this, is I'm curious how if you believe that, well, they're not moral beliefs anymore, but if you're an expressivist, I wonder how it is that you determine how to act in moral situations. Are you just listening to your conscience, or because it seems very easy if say you're a Christian, you
Right.
have a theology, you
Right.
know how to act in certain situations by consulting scripture, but
Right.
if you're really just going by boo yeah,
Right.
it seems like it's difficult to make principled judgments about ethical or moral scenarios.
I mean, I think that's true. I'm not sure what to say about that. First of all, I think really principled judgments about moral scenarios are often very difficult. I don't know. You're going to give me trolley problems or something like that. I'm not sure I'm gonna know what to do. I guess the thing that you hope, I mean, and once again, you're dragging me into a conversation in which I don't feel like I have expert opinions to
Yeah,
offer.
this wasn't meant to draw out expertise. I was just very curious on a personal level.
This all does strike me as well above my pay grade, but I guess you might hope that something like this is true, that that something like scientific investigation might, in principle, make it more and more clear what human flourishing looks like. Okay. The circumstances in which the most human beings feel the most fulfilled, feel good about what they're, I don't know what, okay? That somehow reflection on what human beings are, and a large part of this would be scientific investigation, might clarify what you mean by human flourishing, okay? And that the more you know about that, the more your sentiments will line up with what's conducive to human flourishing. But yes, it will be as expressive as the word expressivism suggests, just expressions of how I'm responding to stuff, okay? But the hope would be that as we know more about human flourishing, the way different people respond to these things will converge with one another more and more. It'll emerge as some kind of fairly general property of human beings what they think flourishing constitutes and how they react to things once they know more about what flourishing constitutes. Yeah. Whether this'll end up making precise distinctions in trolley problems or not, I don't know. I don't know.
Okay, well, David, this was absolutely wonderful. I got so much out of it.
Great. Well, it's really fun. And like I say, I'm happy to do it. I'm happy to, there's lots to talk about. And we always arrive at the end of these things realizing that there's lots more to talk about.
Yeah, so